Hi, I'm Mieke van Hemelrijck and I'm a cancer epidemiologist at King's College London. And together with Professor Ton Coolen, we run the work strand on data management and analysis for ReIMAGINE. And so this is the workshop specifically focused on big data. And so what we would like to do here is first give you a little bit of an understanding of what do we mean with big data, specifically for prostate cancer, and then how does that translate into ReIMAGINE, and most importantly, how do we then analyze all this big data that we collect in our various ReIMAGINE studies? So this is a definition of big data, which I have taken from the IMI website, which is the Innovative Medicine Initiative from the European Commission. And it kind of explains that it's all the data that we can collect on an individual, whether that is personal in terms of demographics, but equally biological information. So that's the information that Gert Attar was talking about earlier in his presentations. It's all the information we collect from blood, tissue, urine samples. We analyze it in various ways, and that also gives us a variety of data points. And then we end up with huge data sets, which can be one line per person in our spreadsheet, but then like hundreds and hundreds of columns for every variable, every marker that we collect data on. And we could even have multiple rows for a patient because we could have repeated measurements over time. And so that's the kind of data that we need to analyze. And so in the context of prostate cancer, there is something called Pioneer, which is a big data consortium funded by the IMI, so by the European Commission. And we are part of that as well. Pioneer, like my group is leading a work package on this big data consortium, and so that's also how we're linked to ReIMAGINE, to kind of learn of how we're using different methods in terms of big data. And so what Pioneer does is it's trying to bring data together from various countries across the world, not just Europe. That could be hospital data, it could be trial data, it could be registry data. And the aim is ultimately to use all that data and improve prostate cancer patient care, whether that is by focusing on cancer outcomes, could be quality of life, but equally, how can we improve the health system to improve the care for our bladder cancer patients and their families? So how does that then translate into ReIMAGINE? So here is a schematic that shows you what we're doing. So we have data that we collect from the various hospitals where we recruit our patients, that then gets entered into a system where we then anonymize the data and we give everybody a research ID. Then all the data get merged on a platform which we run together with Philips, and then the data becomes available for further analysis. And so here is a slightly more detailed overview. So because, as you know from the first presentation, so there is two studies. This is work strand one, which is the work that Hash Ahmed presented. So that's a study where we're going to recruit 1,000 patients. And so we'll have imaging data, clinical data, biomarker data, omics, digital pathology, and all of that gets merged together, gets anonymized, and then that can be made available for analysis. And then we have our second study, which Caroline Moore told you all about. So our screening study where we're almost ready with recruitment. So there again, we'll have imaging data, clinical data, and we'll be able to link that to whether someone then gets diagnosed with prostate cancer or not. So that's just a little bit of a background on what big data is, how we collect data, and so then we are in a position to use that for analysis, which is what Tom will tell you all about on the next slide.
So, to give you an idea of the types of problems that we run into when we want to analyze complex clinical data, specifically cancer data, I just wanted to show you a couple of examples of the types of issues one needs to resolve when doing it. So the first example here is what happens if you merge data sets that come from different hospitals. So imagine here that we have two hospitals that each want to find out whether a given treatment is beneficial to patients or not. So they have two options, treatment A and they have treatment B. And every center gives treatment A to a couple of its patients, and it gives treatment B to a couple of its patients, and it tries to find out whether or not A or B have the highest response rate to this treatment, because they want to find out which treatment works best. So in this table at the top, you see what happens if, for instance, in center 1, they gave to 100 patients treatment A, and they find that 40% of the patients responded. To 500 patients, they gave treatment B, and here they found that 150 patients responded, so 30%. So on the basis of these data, a medic in Center A would conclude that the response rate to treatment A is better than the response rate to treatment B, which would probably lead to treatment A being preferred. So imagine A is one type of drug and B is another type of drug. You would prefer to give treatment A. And now imagine Center 2, a different hospital, did a similar experiment. So in Center 2 also patients were given treatment A or treatment B, but this hospital happens to be a bit smaller. So we have here a total number of patients that is about 280, and in the other hospital we had 600. But imagine that 36 out of the 200 who received treatment A responded, so that's 18%. And they found that 12 out of 80 who got treatment B responded, which is 15%. So overall the response rates are lower in Center 2, which may well be dependent on a location of Center 2, geographical location, or the ethnic composition of the people there. But again, in this center also, the conclusion would be that the response rate to treatment A is higher than that to treatment B. So also Center 2 would conclude that treatment A is the better treatment. So far there is nothing strange in all these data. Now imagine that we would like to combine these data because we think if we have more patients, our inferences and our conclusions will be stronger, will be more reliable. So what we could do, that seems the natural thing to do, is to say, okay, so we pool together all those patients that got treatment A. There were 100 in hospital 1, there were 200 in hospital 2, total number is 300. Out of these 300, 76, we just add those two numbers, responded to treatment. That gives you 25%, which is sort of in between hospital 1 and hospital 2. And we do the same for B. So in total we would have 580 patients who received treatment B. Out of these we see that 162 responded. So that's 28%. And now if you look at this result, something is appearing to be really unexpected and strange, namely we now see, simply by adding up these numbers, we've done nothing else, that the response rate to treatment B is now higher than the response rate to treatment A. And it seems that something tricky has gone on, but there has really not been anything that is not right. By simply adding those, this is what we find. And this has a name in statistics, this phenomenon is called Simpson's paradox, but it is just illustrating how careful you have to be with medical data, or data in general. So each hospital would conclude from its own data that treatment A is better than treatment B, but if we combine the data, we find that treatment B would be better than treatment A. So what is happening here? And what is really happening is that in this type of situation, you have to look also at how likely it is that someone entering hospital 1 would be put into the group that was given treatment A versus the group that was given treatment B. And you would have to do the same for hospital 2. And you have to take into account the differences in how likely a patient is to be put in this group versus that group. And this can influence this type of merger of data, as you can see in this example, significantly. And if you were to do this analysis more carefully, taking into account those differences and correcting for them, then you would indeed find that by combining the data, also still treatment A is superior to treatment B. But you see here how slippery statistics can be. This type of thing really calls for a very careful analysis of any types of decisions that went on behind the scenes. And this happens a lot in medicine. Let me give you another example. In medicine, you very often also find that not all measurements that you could take in the patients are available. So we call these missing values of covariates. The covariates are things that we can measure in patients. So if that happens, then something really tricky can go on, namely that those missing values might not be randomly missing. And that happens again a lot in medicine and specifically in cancer data. And this is an example of real cancer data where a certain measurement, CX, was available for some patients but not all. And here you get curves that give you the probability that someone would survive, given that in this particular case the value of CX was high, and in red for those patients for which the value of CX was low. And in this type of data you would see that therefore the presence of the high value of this variable CX would help the patient to live longer. Now here you see the curve in dashed at the bottom for those patients for which this value was not measured. And here you see that this is not just an average of the other two, but the patients for which this value CX was not measured have significantly worse prognosis. That means that these measurements that are missing are not randomly missing. There's something going on that means that they are more likely to be missing in patients that are not doing very well. Again, this is the type of subtlety that you run into in medical data analysis that would not tend to happen when you analyze, for instance, data in the stock market or anything like that. So medical data can be really tricky. Let's go to the next slide. Now, what else should we be really careful with? The next thing is that we have to be careful in our use and our interpretation of big data. What do we mean by big data? We all agree on big data means that we have a large number of variables, but this can happen in two very distinct ways. So the first possibility is that we have many data because we have many patients from which we have extracted such data, in which we have measured these data. But in each patient, we measure a relatively small number of variables. This is in a way a very benign situation in the sense that there are no conceptual problems. This doesn't cause any problems for statistical methods. The only thing that happens is you need bigger machines, you need larger hard disks to store the data, you need faster computers to analyze them. However, nowadays we very often find ourselves with this type of situation. We have a modest number of patients in our data set, maybe a few hundred, but we have relatively many variables that we can measure in each patient. And nowadays, with the human genome being completed and with all the information that we can now measure that is of a genetic nature, this happens a lot. We can measure millions of variables for each patient, but still, we might only have a few thousand of patients in which these measurements are done. Here, the problems are of a more conceptual nature, because most of the statistical methods assume that it is the first class of big data and not the second. And the intuition that we get from statistical methods is a lot more primitive. And we need to use very advanced modern new methods that were not available, let's say, at the end of the previous century. Okay, now, here's another issue. I want to go with you just to a simple example of the type of situation you can get. There's a website in the US, here's the link, where someone has collected data from many different walks of life, and he has looked at which of these data happen to correlate strongly with one another, so happen to coincide very much. And then he shows these examples, and this is one where he found out that if you look at the age of Miss America, plotted versus time, and you look at the same time at another variable, which is the number of murders in the US by steam, hot vapors, and hot objects, then you see these curves are very, very similar. And if you quantify that similarity, you get a number, it's called the correlation coefficient, and it's really high. Now, if you look at this, you might be tempted, if these were other quantities that were measured, to say, okay, they're probably related. But by just looking at what is being plotted here, they are certainly not related. So what we see here is just a correlation that happens by accident. And this, of course, should not be a surprise. If you measure sufficiently many things, at some point you will find a correlation between variables purely by accident, because it's simply impossible to only find things that are completely distinct. At some moment, if you measure millions of curves like these, you will find two curves that happen to be nearly on top of one another. Now, this is called overfitting, and it's one of the biggest problems in modern data analysis. So, medical data are tricky, and they have become more tricky in the last few decades. And it is for several reasons. I've already indicated a couple. We have the volume of data. We measure many, many more things than we could measure a couple of decades ago. But also it's a diversity of data sources. There are many different types of things we can measure, and they tend to be quite diverse. We can have clinical variables, the usual things, tumor size in cancer, for instance, tumor grade. We can measure genomic variables. We can measure biomarkers, proteins in the blood. We have health records. We can do biopsies. We can make images of tumors and so on. But also, the complexity of all these pipelines that generated these data has increased an awful lot. Some of these experiments are really complicated, and that sometimes can lead to variability between the outcomes of measurements if we compare different medical centers. They just need to have a slightly different make of a specific imaging machine, and these images will be slightly different, for instance. But this is, in my view, one of the biggest problems, and this relates to this overfitting that I showed you on the previous slide. And that is that in the 70s, when many of the medical statistics methods were developed, we usually had data sets with at best a few thousand patients, and we could measure only a small number of things. These days, we may have slightly larger data sets, but we can measure enormously many things. We can measure millions of variables. This is not just genetic, but also in images, there's a lot of information. Now, this is called dimension mismatch, the mismatch between a small number of examples and many, many things we can measure, which increases the risk that you see patterns that are fluke. So it is increasingly important to have methods that see the difference between a real pattern, something that we can use to predict clinical outcome for patients, and patterns that are fluke, that are just accidental. And in addition to the changes in the data that we have, of course, our ambitions have also changed in medicine, because we have so many more tools to measure things in people. We would like to use all these measurements to tailor treatments to patients. So we no longer want to have a one-size-fits-all therapy, which in the past for cancer obviously has been chemotherapy. But we want to move away from this. We want to use all these differences that we can measure in patients to tailor treatments to the characteristics of individuals. And the hope is that by doing that, we will have treatments that are so carefully tailored that a significantly larger number of people will benefit from treatment than what has been the case in the past. Okay, now statistics is extremely slippery. I used to say to my students that it's the most slippery area of mathematics, and it's not because the calculations are difficult, but because it's very easy to make mistakes in interpretation, in how you set things up, how you measure things. And to give you an example of this, just to show you how poor we humans are thinking in terms of probability, there's this well-known problem. It's called the Monty Hall problem. And this is a question that was raised in a radio show a couple of decades ago in the US, where a question was posed, and the question went a bit like this. At the time, there were many game shows that had a very similar format. And in the US, there was a game show by this host, Monty Hall, and they all had the format that at the end of the game show, one participant had won the show, but there was a twist at the end to decide whether or not this person would get a prize. And the twist was this. This winner of the show would be put in front of 3 doors. Behind one of these 3 doors, there was some grand prize, a large amount of money, or a fancy car, or a trip to the Bahamas, or whatever. And behind the other 2 doors, there would be something silly. In the US, they tend to put goats behind these doors. Now, the winner would be asked to select a door. Well, the winner has no choice but to pick one at random because he doesn't know what is behind the doors. After the the contestant has chosen a door, the host opens one of the other two doors. And because there's always only one door with a prize, he can always open a door behind which there is no prize but a goat. Having done that, there are two options left. The door that was chosen by the contestant at the beginning, and the other unopened door. And the host would ask the contestant, you still get one chance to change your mind. Do you want to change your mind, or do you want to stick with your first choice? And the statistical question is this, and that is what was posed in the radio show. Does it make a difference whether or not the candidate at this moment changes his mind and goes to the other unopened door? And at the time, many people thought this is obvious, it doesn't make a difference, and many serious, even mathematicians, made fools of themselves by getting it wrong. Because intuitively, yes, I also got it wrong the first time. I would have said, similarly, it doesn't make a difference, it's 50-50. But if you really carefully work out all the possibilities, what you find to your surprise is that you should always switch, because you always double your chances of winning a prize. And this is a subtle thing. And the mechanism behind it is that this host has given you some information by having opened the door, because there are situations where he is constrained. There are situations where, if, for instance, one of these doors has actually the prize, then he has no choice. There's only one door he can open. And this somehow changes the problem. And if you work it out, you simply find that you always double your chances by changing. Now, this type of situation happens a lot. And we humans are really, and this is a tricky thing. That means that we cannot think naively about probabilities in medical outcome prediction. Now, another question is, how many data do you really need in order to be sure of something? And this is a very similar question to asking, if I roll a dice many times, at what point can I conclude whether the dice is fair or not? And in medicine, there's a clear equivalent to this. If a genetic mutation tends to occur in a certain number of people, I would like to know, is this mutation harmless or is it dangerous? And the way to do this would be to collect many examples. Either I roll the dice many times, or I look at many pairs of people, one with a mutation, the other without the mutation, and I investigate what their clinical situation or clinical outcome is. Mathematically, these are very similar problems. And the advantage of the dice is you can simply do it on a computer. And this is an example which you see. Now, if you have, for instance, a fair dice, then all the probabilities, I can just do a certain number of throws, let's say 2,000 throws. I measure how often do I get a 1, how often do I get a 2, and the fractions of these individual throws I plot vertically. If the dice is fair, then if I increase the number of throws, ultimately each of the throws would occur in the fraction 1/6 of the times. This would be a situation of a fair dice. This is an example where you do it with a loaded dice, where one outcome has a higher probability, namely 1/5. And then you see that until you get beyond, let's say, about 1,000, you really cannot conclude anything yet from such data. Now, and these numbers are very similar to the numbers that you often have in clinical trials. Yeah? Clinical trial is often conceptually very similar to doing a test like this. So you see, you have to be extremely careful. And after 500 or 1,000 throws, these two cases are just zooming in from the previous image. You see, after 500, there's nothing you can say. There's no way to yet conclude that the one on the right was a loaded dice. Okay, so in modern data analysis, data of cancer medicine, what we try to do is we try to quantify patterns that allow us to predict things. And what we want to predict is clinical outcomes. And these could be the time to recurrence of disease, time to death. They could be whether or not someone is likely to respond to treatment, side effects, and so on. And we try to do this from the variables that we can measure in our patients at baseline. And these are genomic, these are concentrations of proteins, for instance, in the blood, or RNA, these are tumor biopsies, and so on. And the key problems that we need to resolve are these. So there is the issue of inference and causality. Very often, most of the methods, they can infer whether or not there's a relation between two variables. Say, if a certain protein found in the blood is high, this often coincides with someone having a poor clinical outcome. What you generally cannot infer is which way the arrow of causality goes. Is the clinical outcome caused by the high concentration of the protein, or is the high concentration of the protein a response of the body to the clinical situation? And this is not obvious. The second one we've talked about earlier, this is this issue of dimension mismatch and overfitting. How can we see the difference between a real pattern and a fluke pattern when we look at so many data? And there's a third one, which also in cancer is very important, and that is that no two individuals are the same, no two cancers are the same, even if the measurements we take are very similar. And this is called disease heterogeneity. And in addition, we have the fact that many people who are, let's say, older, they tend to have more than one disease. And it's not always obvious or not always credible that these diseases would act independently. So you need to take also those things into account. Okay, and I want to end with, I'm not going to show you mathematics, obviously, but I wanted you to have an idea of what the subtle issues are that you have to face. It's not a case of just collecting enormous amounts of data and then pumping it into a computer and out will come an answer. And this also means that naive machine learning ideas or AI ideas will not work, because you have to think extremely carefully about interpretations, about possible relations, about possible variables that you're not even measuring and their potential impact. And where are we heading? Well, we haven't finished the ReIMAGINE project yet, but I can show you an example of the outcome of another finished project, this related to breast cancer, to give you an idea of what we think would be achievable with more advanced statistical and mathematical methods in the area of personalized cancer medicine. This is where we want to go. So this is an example on breast cancer, where we have a method to compute from the data a score that tells you whether a person is high risk, low risk, or intermediate risk for recurrence of the cancer. And this was measured in a very sophisticated way from variables that relate to what happens in lymph nodes. And not just in lymph nodes that contain disease, but also by looking at the reorganization of the immune system in lymph nodes that were not yet affected by the disease. They contain apparently a lot of information. And what was found here is that we have two types of patients, those that have lymph node positive disease and those that have lymph node negative disease. That means lymph node positive are the ones where upon doing a resection of the lymph nodes, one finds that there's already disease in the lymph nodes. Now, what we found by doing this is that by computing this risk score, we found that we can identify a subgroup of the patients that had lymph node positive disease for which the survival prospects, the likelihood of survival over time, were more or less similar to those of the patients that had lymph node negative disease. So these are patients, the dashed line, that did not have cancer found in their lymph node. So normally what we would have done is if a patient was a lymph node positive patient, they would be given a much more aggressive treatment than those that were lymph node negative. But we see now here that we can identify a subgroup for which the risk is identical to that of the more benign lymph node negative cases. So these people here, these women in the green group, should not be given the aggressive treatment because it's not necessary, because their prospects are identical to those of the lymph node negative patients. And we see this in all breast cancers, and we also see this in the really more tricky triple negative breast cancers, which are even harder to treat. Again, you see that there is a subgroup, the green, that have prospects that are similar to the lymph node negative patients. So rather than giving one-size-fits-all treatment to the lymph node positive women, you now have a more sophisticated resolution into low risk, medium risk, and high risk ones. And you can tailor your treatments accordingly. Now for ReIMAGINE, we have different variables that we measure, we have different types of data, but this whole principle of using the sophisticated data that we can measure these days to tailor treatment is exactly the same principle. And I really hope that at the end of the project we can report very nice results in this by using the data intelligently. Thank you very much.